Hello everyone, my name is Aaron Standard, and today we're doing something a little different. We did a webinar yesterday called Designing Production Grade Akka.NET Applications, and GoToWebinar had some issues actually capturing and delivering the recording. Normally we put these videos up on our YouTube channel a couple of weeks later. We're doing it now so everyone can get access to it. I did something a little different during this webinar. Now we cover a whole bunch of best practices and good ideas for how you should go about trying to design, reasonably complex software with Akka.NET actors. But even though I'm probably the most experienced Akka.NET developer on the planet, I make mistakes too. And that's one of the things that we're going to dive into on this webinar today, is that I actually go ahead and show how I took a project that's actually pretty critical for our company and really overcomplicated the actor design. Now, part of the reason why it's still a useful exercise is that the reason why my actor design was complicated is because my domain design was also anemic and too complicated as well. The 12 hours I spent modeling this with actors probably saved us years of technical debt cleanup as a result. So overall, a very worthwhile use of time and resources. But without any further ado, let's go ahead and dive into the content, and make sure you take a look at the description, because I'm going to link to a couple of other videos that I referenced throughout the webinar. So let's get started. Today, we're going to be talking about designing production-grade Akka.NET applications. Now, we've had a whole bunch of webinars and videos we've done that dive into specific Akka.NET features and other little bits and pieces like that. This is going to be a little different today. We're going to be covering basically some of the best practices for how you should try to model software with actors. But the real big thing we're actually going to do today is take a look at a real enterprise-grade project that I've been working on. And that project has some pretty significant problems with how I've modeled it with actors so far. So we're going to actually diagnose my own mistakes and talk about that. I figured this would be a great way for people who are getting their feet wet with actors to kind of learn by example, where even me, I'm one of the most experienced people in the world with Akka.NET, and even me, I make mistakes too. So we'll go ahead and kind of peel the lens back on that and see what I did wrong and what I'm going to try to do differently in my next pass on this project that we're working on. There we go. Our table of contents today is we're going to touch on some evergreen strategies for good application design first. So we're going to talk about the theory first. What should you be trying to do? So we'll talk a bit about that. We'll talk about planning for distribution. So this includes things like resiliency planning, networking, so forth. We'll talk about incorporating failures into our design. This is going to include a combination of human and technical failures. Then we'll also demonstrate basically a little bit about configuration and testing. What should we do to kind of make it easy to configure our applications down the stretch? And then finally, we're going to touch on a real example and why actors are a good fit for that problem. But we're also going to focus on, this is probably the most important piece here, validating our domain model and our designs with actors. That's really kind of the big thing I want to touch on, is that actors give us a fairly low-cost way of making mistakes cheaply so we can learn from it before it becomes a giant flaming pile of technical debt in production. So that's what I want to talk a bit about today. And at the very end, we're going to get into the golden rules of actor programming. These are the things that I think are universally true when it comes to programming with actors. Now, it's not an exhaustive list, but it's the top 3 that I think about constantly. So let's talk a little bit about our project first, and then we're going to talk about the theory. SDKBin is the platform we launched nearly 5 years ago for being able to sell Phobos, our commercial open telemetry add-on for Akka.NET. And we had lots of plans to sell other products and let other people sell products through there too. And all of those have not come to fruition. And the reason largely is that this software was designed with a very inflexible CRUD model, and its billing system is married very deeply to annual billing cycles and Stripe integration. So as a result of some of these decisions that were, these were really important decisions for our real proof of concept we wanted to get to market, it made it really inflexible for us to support a lot of business cases that we need. A good example, like half of our customers that buy Phobos don't use the built-in Stripe integration. They send us purchase orders that we handle through our accounting system offline. We need some way of reconciling that with SDKBin, and the process we have for doing that today is very manual. It'd be a lot better if we had some way of being able to go ahead and create invoices and close them out directly through the SDKBin UI. which is something that we are going to attempt to do in the very code that I'm going to be showing you later. So let's talk a little bit about some evergreen strategies for good actor application design. The first thing we want to think about is designing our actors to be distributable. And here's what I mean by that. There are definitely some actor applications that will run fine forever and ever in a single process. A good example of that would be if you're using actors to paginate, network events and turn them into UI events in a WPF application or maybe a mobile app, you're probably not going to need to worry about distribution. It's a 100% local case. Or maybe if you're, we got some customers in like oil and gas. If you're building actors for an embedded system that stays connected to like a single, a single pump or a single well, well, that actor process is probably not going to be running in a cluster necessarily unless you need some disaster recovery stuff. It's probably going to be there running on site. It's kind of an embedded edge device. But for all of these systems that you might build for being able to run real enterprise software or running, let's say, really large scale systems like meter data management, which would be, aggregating all the data that comes from those oil wells, that type of stuff, you're going to need to plan for your actors to be able to be distributed over a network like Akka.Cluster. Getting this right early in your architecture will make it very easy to transition from like a local first design, which is much easier to experiment with than a big clustered one. You can basically make it easy on yourself and not have to, bite it all off all at once. And the real like supreme rule for doing this is to embrace the child per entity pattern early. We have a blog post on this on the Petabridge website, and you see this pattern emerge organically everywhere in the Akka.NET ecosystem, including in Akka.NET's own internals. We manage things like TCP connections and everything else using this pattern too. The child per entity pattern is basically a way of being able to take a range of entities that are all of the same type. So in this case, some of the STK-bin entities we're going to see today, we have subscriptions, which define access to a product. An account, which is the financial half of a subscription, basically determines if a customer is paid for that subscription to be renewed or not. Then we have an invoice, which is the means by which that payment is secured. And then the payment intent, which is the actual financial transaction with a payment gateway of some kind. So these are all discrete entity types. We are going to model these each with their own unique actor instance. That's what the child per entity pattern is all about. For every instance of a thing you need, you create a self-contained instance of an actor that is the sole owner of that thing. This is very easy to reason about from a programming standpoint, and it is also very distributable. This happens to be how Akka.Cluster.Sharding works naturally. So if you get this to work correctly locally, it'll be very easy to translate this into a design that can be distributed later. So this is like a brownfield project, this SDK bin thing we're working on. We're trying to integrate a whole bunch of actors into a super CRUD heavy system. Therefore, we don't really want to add stuff like Akka.Cluster.Sharding into that mix until we're a little further down the road. Mostly, we're kind of trying to do like some Strangler Fig sort of stuff where we get actors to replace some of these like AutoMapper powered repository monstrosities that are in there right now. Once we replace some of that, then maybe we can start clustering it, sharding it, doing all that good stuff. And that would be great when we can get there. But for the time being, when we're just trying to validate our domain, I do not want to mess with the cluster. I just want to test my actors, test my messages. I'll probably also use things like Akka.Persistence. That's fine, working locally as well. Get all that working locally, use a pattern that kind of can be translated to the network real easily. And the reason why the child per entity pattern does this well is that if I have a cluster where I have several different instances of a process that all have the same hierarchy, what the Akka.Cluster system is going to do, Akka.Cluster.Sharding specifically, is rather than have 100% of entities under a single parent, it's going to go ahead and spread them out evenly, where if I have 4 nodes, each one of them is going to get roughly 25% of all the unique entity IDs that could possibly exist under here. So I'll have a relatively even distribution of state. And if I add a 5th node later in the future, Akka.Cluster.Sharding will automatically rebalance and then we'll have a 20% per node entity distribution. The key to doing this is the child per entity pattern. That makes it so you can switch between a local only mode where you have a local parent actor that's basically pretending to do what the shard region does. And I'm going to show you a code sample of that in a second. That'll allow you to flip over to the live real sharded entity later. The next big thing we need to do to get our system ready for being distributed is think about our message design. Messages must easily and quickly identify what type of thing I belong to. So what type of entity is responsible for processing this message and which instance of that thing. So I didn't use these exact words in the presentation here because it's a language term I heard a lot when I was much more involved in the NoSQL space. But that's kind of not as hot of a subject these days. The term is called a blind write system. And what this means is that when a message comes in to, let's say, a web API or some other point of ingress inside your system, that message already contains all the information you need to route it to its final destination. So there's no lookup tables or all sorts of zigzag type movements to try to figure out where this thing belongs, where it should go. The data that is built into the message itself should be sufficient to answer that question almost entirely. This means that it becomes very cheap to route messages to their correct destination if you do that. Most CRUD systems aren't built that way. People like to use synthetic identities, etc. Now, I'm not arguing to use natural keys. You can make this work with a synthetic key as well. The trick is just not putting it through several layers of lookups first. So make it simple, cheap, and easy to identify which instance of a thing do I belong to. That's really what this is all about. The other really big thing we need for distribution, I had a SaaS customer who kind of didn't do this correctly the first time around, which is actors must be capable of independent reentrancy. Now, what do I mean by that? Well, this is both a resiliency and a distribution thing. If an actor is killed and recreated in a new process as a result of a deployment or as a result of scaling the system up or down, which is something that Akka.Cluster.Sharding will take care of, or if an actor crashes as a result of an unhandled exception, that actor has got to be capable of reconstituting itself and picking up where it left off again. This means the really big thing you must never do is make that actor dependent on someone else telling it to start back up again or telling it to recover its state. Tools like Akka.Persistence, for instance, automatically take care of all this. They will make sure the actor is independently reentrant. What this particular customer did is they made it so there was an external piece of stimulus the actor needed in order to basically start rebuilding its state. Well, as soon as those actors got rebalanced the first time their system scaled up, everything died inside that application. And that's because they failed to do this. So this is a really, really important encapsulation detail you can't overlook. That when the actor starts up, it should use its pre-start routine, or in the case of Akka.Persistence, it'll just do this automatically. It should figure out, how do I figure out what my state is and where do I go get it? In SDK bin, we've got a combination of some actors that are going to be using Akka.Persistence. These are basically kind of like new concepts that didn't exist in the database before. We're going to use Akka.Persistence for them. Old concepts that already have an analog somewhere in our SQL schema, we're going to go ahead and kind of write our own little bits of tooling to help them recover their state using what's already in the database somewhere. So why reinvent the wheel, right? Either way, the design goal remains the same. The actor has to figure out how to do this by itself without being told what to do. Now, the first time an actor gets created, sure, you need to be able to send it some payload that helps the actor figure out, who am I, what do I do, and what data do I need? Fine. The actor should persist that, save that, and be able to recover it in the future. That's what we're saying. This is a good example of being able to kind of create a local child per entity actor. Now, I've posted, I think, GitHub gist to this before, and I'll probably do, I don't know, either a little blog post or something that has a link to this exact source code. What I'm doing here is I am basically stealing the iMessage extractor from Akka.Cluster.Sharding, And I am basically just using it down here. Let's see, yeah, down here and kind of some of this as well. We're basically using Akka.Cluster.Sharding's conventions, the function for starting actors and the message extractor. And we're just using that locally to dynamically spawn actors based off of the entity ID that we process. So this is like not built into Akka.net. This is a piece of like boilerplate code that I use for being able to do local development. I can erase this whenever I want and transition to using a shard region, which is going to take that exact same message extractor and that exact same function. That's what, if I grab my pen again, that's what this is right here. It's going to use both of these the exact same way, just that now it's going to be done over the network, not in a local process by itself anymore. So this is kind of part of planning for distribution, is you want to go ahead and build your system in such a way where I can shift from a local design to a network design once I reach that stage in maturation in my domain model. Trying to build everything for clustering from day one introduces a bunch of moving parts you don't necessarily want to have to deal with just yet. So that's why I recommend starting off with this. If you plan for this and think about it, and also make sure you watch our videos on how tools like cluster sharding works, so you understand some of the mechanics of that. This will make it really easy for you to validate your design locally and then distribute it, which is probably the right order of operations. Now, the next bit of this is also part of planning for distribution, is the network is imperfect. It is a matter of when something's going to fail, not a matter of if. So your software designs that you're building must explicitly account for failure. So some examples from our SDK bin code that we're working on right now. What happens if my payment gateway fails? This happens all the time with Stripe, particularly when we're accepting payments from like European or Middle East customers, where Stripe's going to have a little freak out because it sees a foreign credit card and immediately, and the fraud levels kind of spike in terms of its detection. It might go ahead and return a payment decline method, and all the customer's got to do is retry it again. But sometimes the payment gateway might send back a totally different type of failure message. For instance, we have some customers that use basically it's like a single purpose debit card where they have their payment provider, their like purchasing department can go ahead and issue a prepaid debit card that only has enough money to cover this one transaction on it. We had a case last year where a big European company did it, and they priced the credit card in euros, and the conversion rate against dollars changed, and all of a sudden they didn't have enough balance to actually cover that in their account. And the payment gateway came back with an error message indicating an insufficient balance. We should basically plan on handling those cases inside our design from the very beginning. This is all the weird stuff that makes our software valuable, is thinking through all these things that can happen. Now there's more technical concerns too. Like what happens if my message to run the payment doesn't reach my payment intent actor? What's our strategy for dealing with that? We don't want to close someone's account because we screwed up and forgot to run their credit card. So what do we do to account for this? Here's my favorite class of failure though, because it's the stuff that software developers always overlook and it ends up making software really inflexible. And it's also a giant source of technical debt. And this is also probably the biggest mistakes we made with the first version of SDK bin. What happens if the customer screws up and they don't pay their bill on time? And we also don't want to disrupt their service. No offense to anybody here, but for our corporate customers that have dedicated procurement departments, those people are not always the most on top of their stuff, if you know what I mean. So sometimes we'll have a customer that runs pretty late on paying their bill back. And from the procurement department perspective, it's just kind of, maybe it's standard policy to basically pass vendor debt on for 15 days or whatever. And that's, all well and good, but an automated platform like SDK bin is going to notice that a net 30 invoice is now more than N number of days past due, and it's going to close the account and disrupt service when that happens. Well, that's not great. So we might need some means of being able to go ahead and account for that in the design of our domain, where maybe the publisher needs to give the customer more time if they're trying to get their slow moving procurement department, moving, but they need more time to do it and they don't want to disrupt service. That needs to get worked into the domain as well. Not all failure classes are the same, and the thing I'll put down here is that usually software developers fixate on technical issues over human ones. This is something that we should definitely give equal time and attention to. So how would we go about doing that, like in theory, modeling this project? Well, for human error handling, this is conceptually pretty straightforward. It's got to be captured as events inside our system, or in this case, captured as commands. So in this instance, these are the commands that a publisher on our platform can issue in case they need to resolve a customer service problem. And so we've got two different ways of doing that. One is we can change the termination date of the subscription. So we can basically give them some free time on the plan. The other thing we can do is we can go ahead and actually change the billing period end date. This is basically like giving a free credit. This is like giving someone a temporary hall pass while they sort their problems out with their procurement department. So we want to go and incorporate that into our domain. That sort of human error handling stuff, that's more of a problem you need to address when you're doing your kind of event storming, trying to come up with all the different things that can happen in your domain. You just need to think through all the weird stuff. Other weird things that might happen is stuff like customers using the wrong payment method and wanting to switch after the payment's made. How do you deal with that? Well, a lot of cases you tell them, do it right next time. But, that's all stuff that's kind of got to get factored in. Technical error handling is usually where most of the attention gets paid by developers. So on the left here, I have an example of an interface that represents it's a standard type of response we might send when processing commands for subscriptions. So there's commands for doing things like creating a subscription, renewing a subscription, canceling a subscription, all that good stuff. We have like a standard implementation of this interface, but we also have some custom ones that provide additional color sometimes. A good example for that would be some of the commands that deal with doing customer onboarding or basically provisioning a product access for the very first time. Those have some additional payloads that are a little heavier duty because it has to include things like here's the initial credentials this subscription is going to provide the customer with and blah, blah, blah. Some detail about that. Probably the simplest mode of doing technical error handling is implementing request response with an explicit failure state when that comes up. In our case, our failure state is a enum and a string. You could probably provide a more detailed failure object if you wanted to. We definitely do that around the payment gateway. I'll show an example of that. The payment gateway failure object has a bunch more states and information on it, just because the response we want to formulate to the customer needs to incorporate that. They need to know how to fix it, so we got to include that. Timeouts are always implicit failure states. We don't necessarily know if the operation really failed or not. We should try to do our best to make them explicit. So have some way of telling callers what went wrong and why. And if you can provide hints on how to fix it, good example, in our payment gateway system, we'll provide a hint on whether or not a failure is retryable. That's an example of how they might be able to fix it. Just try rerunning the payment within 24 hours and see if it changes. Or, maybe if the error is not retryable, a good example like the balance being insufficient. Well, okay, maybe the customer's got to go, switch to a different debit card and try again, whatever the case may be. The other big question we got to deal with dealing with actors in particular is how do we handle lost messages? Messages will go missing. That is a 100% certainty over a long enough period of time. They will. So how do you want to deal with it? Timer-driven retries are actually not a bad way of dealing with that. That's primarily how we deal with it inside this system. We have basically a billing schedule that checks all the accounts that have an invoice that's approaching their due date, and we prod all of them once every 24 hours or so. And that'll either trigger opening invoices, changing the invoice's status from due to overdue, and it might also trigger the running of payment intents inside that system. So in that case, if we lose messages, we don't have a complex system for trying to account for that. We basically just wait for the timer to come back again. And if I want those messages to have a recovery period that's shorter than 24 hours,
That's a really easy fix. I change my timer. I change it to 6 hours or 4 hours or every 30 minutes. Doesn't really matter. The system is built to address that. You can also go down the road of having some transactional patterns like outbox, for instance, or maybe you want to go ahead and journal all of your messages using a more reliable delivery tool like Akka.Delivery or Kafka, what have you. You just need to make a decision here on what's kind of appropriate for your business. Honestly, I really kind of like the timer-driven retry system because it does not add a whole bunch of extra moving parts. And there's basically a guarantee that even if we miss the first attempt, there will be another one down the road to go ahead and address it. So it's kind of like missing the bus. You might miss the first bus, but you know there's a second and third and a fourth. And as long as you're not out past midnight, you'll probably be able to get a ride home, you know? So that's kind of my preferred way of handling it. If I have stuff that has really high transaction criticality to it, good example, if I receive money from a customer, I have to dispense product. It's just completely unacceptable for a customer to wait 6 hours in the event that I get funds immediately for them to go ahead and get their product access restored or provisioned for the very first time. In situations like that, I'll probably use a durable queue as my kind of preferred technique. So that'll either be something like RabbitMQ or maybe Azure Event Hubs or Azure Service Bus, Azure Storage Queues, SQS. Any of the above would probably work okay. And I'll probably use a queue polling system that has to explicitly acknowledge delivery there. I would not recommend using that for like every single thing that can happen in your system. You kind of got to choose on a case by case basis where does it make sense. And so for me, the two areas where I almost always use a durable queue are transactional emails, where the customer's got to get that email notification in order for the operation to proceed. So I usually will queue up the content of an email into a delivery queue, and I'll have a processor that just pulls emails off, formats them, and then guarantees a send before it marks that item in the queue as delivered. The other area where I'll always do that is handling money. If someone's paid me something, I've got to make sure we do the right thing on our end. So I'll go ahead and use a durable queuing system there. Otherwise, for things like specific activities around, I don't know, issuing an invoice for the first time, if I miss it the first time I do it, I'm not going to freak out. I'll go ahead and let the timer try to catch it the next time around. All right. Next thing I want to touch on is configuration with Akka.Hosting. So I had a chance to basically refactor an older application that was built before Akka.Hosting existed the other day. And it's just amazing to me how much this simplifies the process of trying to compose an application together. Akka.Hosting scales really well with domain complexity. So if your domain is big and complicated and you have lots of different services that all interdepend on each other, or maybe you just have lots of different actor types that all have to kind of participate together in order to do your thing, having a little static configuration method for here's how I configure my financial account actor. And look, I'm using my generic child per entity parent. I'm using my message extractor. I'm using Akka.dependency injection to resolve the constructor arguments for this actor. And then I'm registering it into the actor registry right here. This sets us up for being able to inject this actor into things that are not Akka.actors if we want to. The actor registry will, and the required actor will help us do that. We have a bunch of literature, the new Akka.net bootcamp that explicitly shows how to do this. And it's also in a bunch of our code samples that you can find anywhere. We use this pretty heavily in all of our public stuff these days. The other thing that is really good about using these static configuration methods, now this is a different one than what I had on the previous slide. This basically calls that method plus two others just like it to spin up 3 different top-level actors, different parts of my domain. This makes it really easy for me to plug into the Akka.Hosting test kit, which I have right here. That's what this is all about. I can go ahead and say, you know what? I want to use the exact same configuration that I have in production, and I also want to use that during my tests. And I want to make sure that when I'm working with, in this case, payment intent actors, we're basically trying to make sure that they do what they're supposed to do when we're trying to run a credit card or receive money from a wire transfer or whatever the case may be. It makes it really easy for me to go ahead and make sure that the same way I'm running this in production is the way I'm going to run it locally. And in this particular instance, I don't have any configuration or settings classes yet. I haven't kind of gotten that far in the design. But as you saw when we were working in Akka.NET Bootcamp 2.0, which just came out in February, you can do things like pass in configuration objects to these methods here and do things like turn clustering on or off if you want to. That's a whole nother facet of Akka.Hosting that makes it really convenient, is you can go ahead and toggle whole feature sets on or off if you want. The other thing we want to try to do as part of like a general best practice for working with actors is we want to try to extract business rules from actors and test them independently if we can. All of our business rules around dealing with like when do we open an invoice are actually fairly complex, because that kind of depends a bit on the billing method the customer uses. And we also have to look at things like what state the account is in and whether or not the customer was previously using a billing method that had a really short lead time and they tried scumming the billing system by switching to a long lead time. So if someone tries to go from using a credit card to using a purchase order in order to get net 30 as part of the terms there, we have to detect that and tell them, nah, sorry, dude, like you should have done that before you got within 30 days of the invoice coming up. We got to not change our invoice due date because of that. So there's a whole bunch of business rules that are fairly complex in how we deal with this billing stuff. And that's not because I'm trying to be an architecture astronaut and create a whole elaborate framework for doing this. It's because this domain is naturally complicated. And depending on what you give your users the freedom to do, there's a lot of different edge cases you're going to have to test. You should treat your Akka.NET actors like infrastructure, the same way you would an ASP.NET controller, for instance. The actors' business rules and state, ideally, we should try to decouple them, represent them as independent state objects, and test them independently if we can. That'll ultimately reduce the amount of complexity in your testing system, and it's a lot faster to test that way as well. Now, all that being said, that usually can't be done 100% perfectly. The reason being is that one of the things you're probably going to want to do after you process a command or after you receive an event is there's probably some side effect that your actor is responsible for doing, such as messaging another actor or writing an event to a queue. Well, in that case, then you're probably going to need to have a separate set of like more integration tests or whatever to go ahead and kind of test some of that functionality out, because you can't really easily separate that into its own state object. So that's kind of a bit of a distinction there, which is ideally we should try to do this, but it's probably not going to be perfect. And you certainly shouldn't try to make a giant ball of mud separating actor state from the actor if that proves to be more trouble than it's worth. So don't treat this like a global maxim. Just kind of look at it as this is an ideal thing to do and there's good reasons for doing it, but don't fight the framework. That's what it turns into. Now, we're going to go ahead and switch gears a little bit now that we've kind of talked a bit about the big picture, broad stroke stuff. Let's talk a little bit about what we're going to try to accomplish here, which is building a payment system. So we have to support multiple payment providers. That's probably the biggest requirement that we have. And all these providers don't behave the same. So a really good example of this is lead time. How much time do we need to issue when should we issue a payment intent if we want to get paid by the due by date, right? So for purchase orders, it's going to be net 30. For credit cards, probably going to be same day or pretty much instant. If we ever ended up supporting electronic bank transfers, that'd probably be a net 5 sort of deal, where it'd take 5 business days for a bank transfer to go through. So this is something that's got to be factored in to our design. On top of that, we talked earlier about having to account for human error. We have to have some way of reconciling that inside the system. Right now, STK-bin is basically an unstoppable juggernaut that it has a schedule it's going to stick to. And if you deviate from that schedule, it's going to be a lot of work to go ahead and kind of clean that up. And that's unfortunate. It's one of the things we're trying to change. Therefore, you want the new system we're trying to model to have some concept of a grace period in it, where even if a customer didn't pay their bill on time, you don't want to necessarily kneecap them right away and disrupt their business. You might want to go ahead and give them a number of days to try to rectify the problem, or at the very least, give them a number of days to contact the publisher, the person, which is the organization who's expecting the funds, the money, right? You want to go ahead and basically give them some means of trying to rectify this without their business getting disrupted. That's just a good business practice. We have to be able to support monthly and annually recurring payments. We can also support one-time payments too. That's actually a lot easier than supporting recurring ones. We have to provide descriptive touch points with customers. One of the things our system doesn't do a great job of today is doing things like proactively contacting them when, let's say, a payment is coming due, or another example of this might be contacting them if the publisher wants to change pricing, which is something that the platform doesn't really incorporate right now. This is all real world stuff that should just be built in as sort of a first order citizen inside the system. And then finally, I mentioned down here, you got to prevent customers from scumming the system. So doing things like trying to get additional unpaid time by changing billing methods or doing whatever. Generally, this is actually fairly easy to prevent a lot of this stuff, but you just had to make sure it gets written down on the requirements somewhere. Got to do that. This is a little entity relationship diagram of all the different stuff that eventually has to make it into this billing system. Now, we're not going to go through all the details on here because I don't want to make everyone's eyes glaze over. But what I wanted to demonstrate is this domain is complicated because the real life is dealing with tax, dealing with all the different things that had to be provisioned when a customer makes a purchase, dealing with, let's say, issues like proration when a customer wants to switch from one billing plan to another. This is all real stuff that actually happens for real because that's how business works. So that's all got to get modeled into our software. Wishing that real life was simpler is not a good strategy for modeling software. So next thing I want to talk about is why actors are actually a great fit for this type of problem we're dealing with. Actors are not just for building super low latency applications. They are great at that. And they're great at building low latency applications because they're stateful. They have the ability to take data and make the source of truth of that data their own memory, make it their properties and fields. That means they're acting at a much higher level of I/O than a CRUD system might be, and they're also not serializing and going over the network, et cetera, nearly as much. So actors are also, however, a great fit for modeling workflows, which is the big problem we have in this system. These are slow-moving workflows, but there's a bunch of them, and they all have lots of different little state descriptors that make them a little complex. So actors are really good at modeling that. If you haven't seen our video on behavior switching on the YouTube channel, you should go check that out. That's kind of going to be our big workhorse for handling a lot of this stuff here. It's actors, behavior switching, plus their ability to go ahead and express things as event-driven programming, make them ideal candidates for building state machines, which therefore is a great way of modeling a workflow. So this whole subscription renewal process, that's one big workflow. But the sub-steps that we're looking at, such as how to manage an invoice and then how to manage a payment, these are subflows that are all basically composed together. Another thing actors are really good at is composition. That's what child actors are for. Now, in this case, we're going to use separate top-level actors so we can shard them. But child actors are a great natural extension of a lot of this work that's happening here. So actors are actually quite a good fit for dealing with these problems, even though it's not a super high-performance design. If we wanted to talk a bit more about like low latency actor programming, our webinar we did on real-time Blazor UIs last year with drawtogether.net, that's more of a good fit for that. We're talking about, taking single-digit milliseconds to go ahead and synchronize everyone's copy of the same SVG on screen at the same time. Actors fit really great for that too. But in this case, rather than a streaming system, we're building a workflow-driven system that's driven by payment events, time-based events, and all sorts of business rules that kind of shape a customer's subscription. So we kind of talked a bit about this. Now, to model our domain, we're going to do a little bit of domain-driven design here. The first is that customers have financial accounts. These determine the balance of payments needed to maintain access to one subscription. Each subscription gets its own financial account. They kind of represent different access to different services. So if you're a Petabridge customer, you might have a financial account that represents your Phobos subscription and maybe another one for a support plan. They're technically separate financial accounts. Financial accounts receive invoices. An invoice must be paid in order to keep the subscription in good standing, which keeps access to the products. Invoices are completed with payments supplied via the financial account's chosen billing method. So by default, we're going to go ahead and support purchase orders. We're going to support credit card payments with Stripe. And then we might also support credits that are provided via the publisher. So if I want to give you a free trial, or if I want to give you additional time on your account for whatever reason, I've got the ability to go ahead and kind of top off your account as a publisher on my end if I want to. So here's our initial theory. We talked at the very beginning about the child per entity pattern and how that's a great way to make state distributable, a great way to encapsulate errors, and there's lots of huge advantages to doing that. So the way we would take that theory and apply it here is, let's make each one of these their own actor. All right, that seems like conceptually pretty straightforward. So here's what we're going to try to do as part of design validation. In my opinion, this should be like a negative validation exercise. Find things that don't work and then don't do them. We want to try to operate from a regret minimization framework perspective. My biggest, of all of my literature I've kind of put out online, on my personal blog, or on the Petabridge blog, I've talked a lot about the idea of preserving optionality inside your design. This is basically the freedom to be able to change how things are done without destroying stuff, is what that basically boils down to. So part of that same philosophy is when we're validating a design, we should be asking the question, what could go wrong with it? And is that worse than the alternative? What are some things that we're going to be worried about here? And as a manager of other engineers, my biggest thing I worry about is no one being able to figure out what is going on and how to fix it in a reasonably short period of time. Optimizing for human time, and I guess these days AI time, is kind of my first order, regret principle I look for. So what are some symptoms specific to Akka.net we want to look for in our design that would invalidate it? Too many moving parts is probably the biggest one you want to look for. If you've got a whole bunch of moving parts and lots of different actors that all have to talk to each other, you should really take a good look at that and decide, is this really necessary? Because if it isn't, then you've got to simplify. You've got too much stuff going on. The system's got too many moving parts. Every moving part you add is going to be a piece of technical debt you got to support. So be very judicious about that. Too much repetition in messaging protocols. Now, there's going to be two different meanings of repetition here. One is that you see lots of events that look the same, but they have different types. A good example you're going to see in just a second is we have several different events that all deal with a billing method being invalidated, and also several different events that deal with a payment coming in. That is smell inside your domain. It means we probably have an anemic model somewhere in here. We went overboard. We have two more actors than we need. We need to consolidate when that happens. The other thing you want to look at for repetition is not just the message types, but how frequently we're using them. If you end up building a really chatty messaging protocol by accident, you probably have a state design problem where someone doesn't have information it should probably keep. That's usually what that means when you see that show up. So we want to sniff that out. How frequently are we sending messages around? Now, in a system like DrawTogether, where we're doing lots of streaming, we're blasting tons of messages that represent changes to the content that's happening on screen. That's not the type of message I really mean in this case, because those are real events that are actually happening on a user screen. That's fine. In my case, you're going to see that we're doing a lot of checking to see if billing methods are valid inside our system. That's a problem. That means that we have a design flaw where I have to ask, is this billing method valid before I do something with it? That's stinky. we need to have we probably need to invert control and have basically like a billing method and validation either happen in a single critical location, or we need to push a method to all the affected parties and let them know that billing method isn't going to work anymore. So we got to redesign that if there's a problem. And then last thing we got to look for, this is a classic domain-driven design issue, look for anemic models and actors. I've used the example in like our design patterns training before. You don't need an actor that does string formatting. Yeah, that's a good example of like a super anemic actor. Well, even if you're not doing something kind of obviously absurd like that, it's still very possible to create anemic actors where there's way too much actor infrastructure and not enough actual work for that actor to do. Therefore, you end up creating a lot of work by principle of having to just design messages and events for it. So we want to try to avoid that. The other thing we want to look for, goal number 2, find things that show promise. One of the things we did really well in the design of SDK-Bin's new billing system is one of the requirements we wanted to add for the future is being able to provision types of products that aren't just NuGet feeds. We want to be able to provision things like support plans or provision API keys and that sort of stuff. We came up with actually a very good design for being able to do that as part of this. So it's not just finding things that don't work. You want to find things that maybe they're not perfect yet, but it looks like you're headed in the right direction. And the goal is, let's do this as cheaply as possible in the shortest amount of time. And that's what actors are really good at helping us do. So let's dive into some code and see where things went. Let me pull up SDK-Bin's code here. This is the new code I'm working on here, sdkbin.domain.billing. This relates to a couple of other domains. We have one for provisioning our NuGet products. That's already been validated. That design's good. We have our product access area here. We have our subscriptions domain. These have both been validated. They're in good shape. The billing domain's the new one that we're working on. Let's take a look at our, let's take a look at our financial account state. We'll start with this. So we have lots of good notes about how this matches with subscription state. They both use the same identifier and how this kind of represents the other half on there. This is sort of the subscription is more of the functional half, like do you have access to this product? The financial account is designed to basically determine have you done everything you need to do to maintain that access. And we have it's basically just a little immutable record object. So that has, let's say, our transaction identifiers, our billing method ID, a set of active billing plans that are available for this invoice. So this is going to be our line items that we're going to generate later. We have a little invoice history on here. We know when our next payment date is. We know when our last update is. And we have some information about whether or not we have a current invoice. All right. Relatively simple data structure. We don't have anything in here that deals with, let's say, like permissions. We don't have anything that deals with the specifics about which product features need to be active or any of that stuff. That is all relegated to the subscription actor. So we're not concerned about that here. Next, we have, and don't worry, Writer is in the process of reindexing everything. So my error count will go down here in a minute. Here we basically have a standard messaging taxonomy that's very close to what you've seen us do in a lot of other presentations. We have an account event, which implements our I with account ID. And our account ID is a value object that wraps around, in this case, a string that kind of represents the user's subscription. All that is all well and good. Go back to here. So we have I with account ID. Then we have some of our account events. We have a create event that basically represents the account being created, billing method changed, billing method expired, billing method invalidated, all this jazz down here. We also have commands. Commands are a request to do something against this domain. So we're going to go ahead and try to create the account, change the billing method, change the billing plan. You're kind of probably starting to see a pattern here. If we take a look at the account state, you'll see that we have this process command async, which takes it's an extension method on the state object, so it's a pure function. We pass in the state, we pass in a command, we pass in some dependencies the command needs, namely access to a billing method reader and a subscription invoice provider. This is basically just kind of a thin abstraction around talking to the subscription actors. And this will produce a account command response and a number of events. There could be 0 events in the event that this is a illegal command. So a good example, if someone tries to create a financial account after it's already been created, we respond with a failure and then don't produce any events. And you can kind of get the idea that the whole idea behind this is to run our business rules to validate whether a command can be done. We then create events that kind of describe what's going to change after this command has been processed. And let me close this down here. And then we have this apply function where we take the event and we apply it to the state. And the state will go ahead and incorporate all the changes related to that event. And we'll go ahead and use this to basically like side effect our state here. And then as a result of that design, our actor is pretty skinny. Has some, this is a persistent actor. We pass in a subscription ID as our primary key. We take a dependency on the invoice actor as an I required actor in the constructor. And we have our little service provider. We create our state. We go ahead and do all of our recoveries to go ahead and rebuild it. And then we have our command processing here. We'll go ahead and persist events, let the responder know if those are successful. I'm missing some event handling here for being able to do side effects and notifications. I just wrote this code like yesterday. So it's kind of, the bits are still a little fresh here. But what you can see is that we've repeated this exact same pattern in several places in our code. We do the same thing with the invoice. We also do the same thing with the payment intent. Let's see if I can find that. Payment intent down here. Same idea, all kind of following the same pattern. Now, this seems very nice in DDDE so far, but let's take a look a little bit closer at how we're doing some things. If I take a look at my financial account state, I have a unit test for this. Let me go and find references to it here. Financial account state specs, here we go. I've got a nice unit test that comprises of, let's see, how many total tests do we have here? Give this just a second. 31 tests that cover all sorts of various states, substates, and changes, etc. And the basic idea down here is that we're going to go ahead and basically see what happens when we're in an empty state and we try applying these commands to it. What happens when we're in a do state? We apply these commands, et cetera, et cetera. One of the things that you're going to notice is that there is a ton of duplicated functionality between the financial account, the invoice, and the payment intent. Specifically, probably the biggest piece of duplicated functionality is figuring out, have we been paid or not? We have this on the financial account, we have this invoice status changed event where it basically has the invoice's old status and its new status. And then on the invoice event side itself, we have nearly a duplicate of that. It's just a different class that owns it. Invoice accepted as paid, invoice voided, etc. The invoice class can also go ahead and receive, if I close this down here, we can receive payment events. And one of the payment events we can receive is receive customer funds and receive payment intent completed. And I'm not going to bore you with all the details, but the picture I kind of want to show you here is that I mismodeled this application. And this is all code, by the way, I've written over the past week or so. So it's not like this is, well, let me rephrase this. I started writing this code months ago with the financial account, but the payment, and I also kind of scripted out what my model of what it should look like, all the different entities and everything. All I did was I designed the event handlers and the events themselves. And here's how I would score my own design. The fundamental messaging taxonomy is good. This is a formula I use everywhere. Command, request to do something. Event, a thing that happened. The difference between these two is a command hasn't happened yet and can be validated. An event has already happened and must not be validated. It simply has to be incorporated into the state. A query, which is a request to read something. A response. This is basically like a reply you would send for doing request response. You can use a response for a query or a command, typically. That's good. That's a solid messaging taxonomy. That's easy to follow. It's repeatable. We've also made it very easy to identify which messages go to which entities. We use, if I go back to my code, this like I with payment intent ID. If I go to invoice commands, I with invoice ID. We're pretty good at doing that. Makes it very easy to identify which type of entity it goes to and which instance of that entity. And it's also easy to distribute these messages over the network. They're all very, because of basically this point here, because of this is also true. We've made it very easy to work with Akka.Cluster.Sharding, which is good. Simple identifier system. And yeah, the intent of the design, generally pretty understandable. But this design has more that's bad with it than good on net balance, in my opinion. The biggest thing is there's lots of message duplication. There's lots of different events that all say the same thing. Did we get paid? Or should someone need to pay us right now? And this is kind of a symptom of anemic actor design. When you start seeing this show up, you tried to fit too small of a thing into too big of an actor, basically is what that usually means. So that's a problem. This is going to ultimately result in a lot of maintenance overhead, having to go and say, okay, if I need to update the payment intent complete message, then I've also got to update the invoice status change method, which means I've got to change the account status change method, which means I've got to change the subscription stat, all that sort of stuff. There's also too many things that kind of rely on timers inside the system, lots of retries and backoffs. I didn't even show all of that. But if we take a look, for instance, at like the payment intent system, let's see. Where is attempts on here? Yeah, here we go. So we have a whole bunch of business logic that deals with like how many outstanding attempts there are remaining and how many times can we retry this payment attempt and blah, blah, blah. That's trying to debug that is going to get annoying because there's timers on the payment intent actor, there's timers on the subscription actor, there's timers on the account actor. There's too many of them. Having a timer-driven system is a good idea, but only if it's traceable. If it's untraceable, because lots of things are all independently timed, but yet those entities have relationships on each other, that's going to create a bit of a problem. And that final problem is, let's see, I guess I mentioned it in the next slide. The final problem is the daisy chaining between the actors. So on the design of actors themselves, what did we do well? These actors are really skinny, which is good. They have a minimal amount of domain logic contained in them. That's generally pretty good, which makes it very easy to test our business rules. And the actors are all designed to be independently reentrant from each other. So if I pull up my source here, you can see that most of these actors, the new ones, like let's find the payment intent actor. Scroll up here. This is a persistent actor. So Akka.Persistence has us covered there. But if we take a look at like the subscription actor, this actor has to adapt data that's already written in like SQL Server today to kind of do its job. This actor has an interface, this I product state subscription persistence. This is basically an adapter around our old CRUD design, is what this is. Now, when this actor first boots up, and it's, let me find it, on receive state down here, we're going to send ourselves a recover message that's going to have us load this data from the database. And after we load it, we can go ahead and see what type of subscription we're running, which allows us to get access to the provisioning service we need to kind of do things like extend a user's NuGet key or invalidate that NuGet key if their subscription is being canceled. Kind of whatever the case may be here. Let's just go and do that. And if I go down here to this code, we're just using things like keyed services in Microsoft.Extensions.di to get the right provisioning service available. We're going to eventually add aggregate subscriptions where there might be several different benefits that all get provisioned at the same time. You might get a NuGet feed and an API key and a support plan all in one go. We would go ahead and just loop through those and get all the provisioning services and aggregate them together all in one go. And that's actually a pretty solid design so far. The big problem we have is the daisy chaining of actor interactions. The likelihood, and I gave you kind of a little workflow example here. The likelihood of something going wrong in this design increases the more hops there are in the messaging process here. So this isn't a problem when you have something like cluster sharding per se, where you got to talk to the shard region region's got to find the other shard region to talk to, then that routes to the shard, and then that routes to the entity. That's kind of like a very like directed acyclic graph that's very linear looking. That's fine. It's the fact that these are these big communication cycles that have to go down the chain and then back up the chain again and then down the chain again. These sort of like real like a sort of cyclic looking communication chains. That's a code smell if we want to try to avoid it. Now that may not always be possible. There's cases where actors like cyclically talking to each other is probably the right design for the domain. And there's probably is going to need to be some of that here, but we've overdone it. There's way too many actors involved, and they're saying very little, which is why we have that anemic messaging model as well. Our state is very duplicative as well. Everyone needs to know about billing methods. That seems like a problem. If billing methods can be invalidated as a result of expiration or as a result of a customer explicitly canceling it, I shouldn't need to synchronize that across 3 different actors. That seems crazy to me. So that's a bit of a problem as well, that we need to know about billing methods everywhere. This, again, is kind of just reflective of basically this is like not an anemic actor problem. This is more of choosing a bad boundary is what I really did here. The other thing is everyone needs to know about the status of payments. This kind of makes me think that we put way too much emphasis on the payment intent when really what that is kind of a long-running async callback is what that is. I create a purchase order and that gets emailed out to a customer, and the publisher is going to have to either manually mark that as closed when they get a wire transfer, or if at some point in the future, a payment provider like Stripe kind of supports the ability to record that for you, maybe we could automatically close it. But either way, we don't need to have a whole separate actor for managing that. There's just not enough going on for that to be that big of a deal. The other thing I'd point out is that we have too many ways of persisting things right now. We're using Akka.Persistence for some stuff. We're using our old CRUD design for others. We probably need to pick a strategy and just move forward with it at this point. Looks like I messed up my PowerPoint sequencing here. Whoops. Some other things that are good and bad about this design. Our way of dealing with different product fulfillment types and payment providers, that actually, from a design standpoint, is pretty good. We did a good job of basically differentiating between those. The design for distribution is good. We incorporated failure states into our designs. That's all pretty good. But on the bad column, we committed the classic .NET sin of going overboard with too many projects. We should probably consolidate those. We also probably need to make a firmer commitment on the persistence strategy. I also made kind of a bullet point here saying the reason why we didn't do that is because we were trying to validate how things should be organized, which is upstream of the question of how do things need to be persisted. So we were intentionally trying to hold off on that. So if we want to rethink our design, here's a couple of big takeaways. And you've heard some people who give talks on like our community stand-ups mention this. We should probably use domain aggregates inside some of our actors rather than individual entities. So payment intent should probably be a function of invoice rather than its own separate actor. That would eliminate a ton of code and events right there. Financial account and subscription should probably be merged together. All the money handling concerns can be pushed to the invoice, all the debits and credits that way. The financial account just needs to keep track of whether we need to issue an invoice and whether that invoice has been handled. So we can simplify that quite a bit. The other thing we should probably do is separate our operational and analytical persistence. Here's what I mean by that. If I want to have a ledger that kind of shows the balance of payments inside this system, since we are dealing with money, that can be a projection from the events that these actors process. So having basically that sort of separated into its own lane actually eliminates a ton of the event data that's inside the system. So rather than worrying about how to construct a ledger from have the events worry about that, have a projector figure that out and lay that out into a table somewhere. That would probably be a really good idea. Now, you know what wouldn't be a good idea? Building a framework on top of everything. What I've done so far is, I've taken a pattern and I've repeated it in a bunch of ways. And one thing that's great about that is if I need to go and change something, like I need to change the way my payment intents actor handles, processing failed payments, I can do that independently from the base actor that handles invoices. Or, if I need to use an adapter for referencing old data from SQL Server versus using Akka.Persistence somewhere. I've got the freedom to do that because I don't have a unified behavior model that kind of forces me to do that. Building a framework would not make this easier. No, what we need to do is simplify. We need to consolidate our actor designs and consolidate our messages and have fewer moving parts. Which brings me to our closing chapter here before I take some questions, the golden rules of actor programming. The first thing we should do is keep our problems small. Don't reach for overarching grand solutions in your design. Focus on achieving success through well-scoped, well-tested, loosely coupled interactions that happen in small areas, and then gradually compose them into bigger features and solutions. This is what I got wrong in my design, is I did this, I did not do this. So, lesson learned. And that's, by the way, this is something I already had done successfully on other projects, but I basically went ahead and I overcomplicated the number of components that all needed to be involved inside my payment system. Oops. I should probably go ahead and rethink that and start with something a lot simpler and then gradually compose it as complex as it needs to be. Draw Together, which we've talked about in our webinar that we did a year ago on Blazor, and we've done some YouTube videos on it, is a much better example of where we've done this. All the problems are scoped very, very well in that system. And I've got a video I did all about this called Think Locally and Act Globally. That's on the Petabridge YouTube channel. That will give you a lot more details on how to do this, focusing in on kind of a microcosmic example. So keep your problems small is my first, and the first golden rule. The second, have clear message taxonomies. Command, event, query, response. This is a pretty universally applicable pattern. No reason to overcomplicate it. Combine the scoping messages clearly and quickly around quickly answering the what type and which instance question. So this works pretty well. Give it a chance. The other thing that I'd like to go ahead and mention is I try to avoid complex keys and entity IDs that require frequent lookups if I can. Now, sometimes this is inescapable. So for instance, we had a customer ask a question in Discord the other day. They're trying to build an adapter from one ERP system to another, and they have two different sets of keys, one for the old system they're migrating from, another from the new system they're migrating to. In that instance, a lookup's probably inescapable, and that's okay. Don't break your back trying to avoid doing that if you can. What we're just saying is, if you have the option not to do that, choose not to. That's really kind of the way you should take that advice. Finally, we didn't really touch on the concept of serialization and Akka.Remote that much because this design was being validated at a stage before any of that's necessary. And that's, by the way, where you want to be designing it. You want to design it before you're dealing with the network, before you're dealing with persistence, if you can. But this is a really important, first-class design principle you need to get right from day one to have the best chance of succeeding. Extend-only design is the way to work. Now, extend-only design is not just for Akka.NET messages. It's also very, very, very applicable to your SQL Server schema. You want to design things in such a way where you're extending designs that already exist in a manner that is not destructive. So you can add a new optional field to a wire type or add a new wire type that wasn't there before. Conversely, if you need to translate that into SQL speak for a second, this means adding a new nullable column or a column with a default value. That's optional. And so if that column is not populated, nothing bad happens. Likewise, this could be adding new tables. What you don't want to do is do destructive stuff, taking things away that people depend on currently. This is going to basically result in destroyed data. It's also going to make rollbacks a lot harder if there's a problem. We want to avoid doing that if we can. So embrace extended design everywhere. So upgrades and rollbacks are very thoughtless. It will just work. This is one of these practices that once you get into it, it's very easy to go ahead and do things that were hard before. The big takeaway from an Akka.NET point of view for this stuff is you've got to use schema-based serialization. Protobuf is probably the lingua franca for this. There's other options too, like Captain Proto and some others that are out there. But schema-based serialization is probably the best tool for reasoning about this. We mentioned this in our Akka.NET 1.6 roadmap. We're actually trying to automate the process of generating this for you as part of Akka.NET 1.6. We'll see how well that goes. We've had some early prototypes on it, but we haven't really fully rolled it out yet, of course. And you should see my blog post on the subject here, all about extend-only design. This will kind of help break it down for you and talk a bit about why it's good, why you should embrace it, and also why developers have been using it for 40 years. So that'll close it out for today. I'm going to go ahead and try to answer some questions real quickly. Let's see. First question from Athanasios. If a retryable item is not persisted, how do you handle retries? Durable queue publishing might fail. And he mentions he's a transactional pattern type guy. So if a retryable item is not persisted, how do you handle retries? Well, one way of being able to go ahead and handle that without persistence per se would be using replication, where multiple actors all have the same piece of information and are spread out throughout the system. Using a tool like distributed data, for instance, might do that. Persistence is definitely the cheaper option, though. That's why we persisted things like the number of retry attempts that were pending on the payment intent. That kind of helps us keep track on the state machine of like how many times can we retry this before we need to give up. If I try running the same credit card 3 times in a row, 1 time per day, and it still doesn't work, pretty sure running it a 4th time is not going to help, right? And then another question from Athanasios. Isn't it better to derive the actor entity IDs by its path name, given the pending migration to sharding? We're kind of doing it the other way around. We're deriving the path name from the actor's entity ID. That's the right way to do it, in my opinion. So if you take a look at, actually, I guess I could scroll back up to here. If we take a look at the child per entity parent, we are generating the actor's name here. We're generating the actor's name from the entity ID. This is also what cluster, we should, by the way, technically we should be URI encoding this, but whatever. But this is also how Akka.Cluster.Sharding works under the covers as well. So I would definitely recommend doing that. Let's see. Do we have any other questions written into GoToWebinar? If not, I can go ahead and let you guys use the raise your hand feature if you want to go ahead and open your microphone and ask a question that way. All right, question from Alexander. What is the best way to architect a workflow which requires timers and persistent actors, meaning the actor needs to be able to restore its timer after possible redistribution? That is a great question. In my opinion, the best way to go ahead and do that is probably not to store a dupe. Well, how do I put this? There's a couple of sticky wickets when it comes to storing timers. So one is you could use something like Akka.actor.quartz to use quartz.net to schedule stuff. That's kind of not my preference. I'd probably rather stick that data in the actor that has the scheduled thing it needs to do. What you could do is basically build a little data structure that has if you wanted to do timers based off absolute times, you could just store the date time offset and basically calculate a duration from now to then to go ahead and do it. Another option for doing this might be to use a deadline structure. Let's see, for instance, if I have, looks like I don't have the Akka.NET code open. Let me see if I can find it real quick. Yeah, I'll go ahead and do one here. Deadline. Do I have a deadline type in here? Yes, we do. In Akka.remote. This really should be a private API, but whatever. Time span, seconds 5. Actually, when does this take a deadline? This takes a date time. Okay. Let's go ahead and do date time. UTC now dot add, I don't know, 5 minutes from now. You could persist a deadline like this and then check to see if we're overdue and go ahead and basically schedule to run that way and persist it. It's basically a really simple kind of Boolean wrapper around a time span. The other thing we actually do kind of in more modern versions of this code is rather than having an is overdue property, we have an is overdue function that can take a time span in it. That allows us to virtualize time a little bit. That'd actually be a good thing to write a blog post about at some point. But that's one thing I would consider doing is persisting a deadline. When the actor boots back up, it can check to see, are these deadlines overdue? And if they are, it can go ahead and immediately schedule that activity to execute. In the event that the deadline is not yet due, it can compute a time span for when that's going to be due in the future and go ahead and stick that inside the actor's I with timers call to go ahead and basically just reprogram it that way. Let's see, does anyone have their hand raised, or are there any other questions I should take? No? Well, hey, thank you all for your time and attention today. I really appreciate it. You should get a recording of this webinar after the session is done. Once again, thank you very much. I really appreciate it. And we will also put this up on the YouTube channel after a week or so as well. So thanks for your time, everybody. If you have any questions or comments, please feel free to reach out to me in Discord, or you can send us an email at hi@pettibridge.com. Thank you very much for your time today. We appreciate it. Bye-bye.
Well, that'll do it for this video. If you found this video useful, please don't forget to check the description to find links to other resources we may have included, so blog posts, GitHub code samples, other videos, so on. And as always, don't forget to like and subscribe and ring the bell for notifications. We'll catch you next time. Thank you very much.